Okay, everyone. So we're going to finish the course with, and we're going to finish off with power series and lead that into Taylor and or Maclaurin and Taylor series. So basically, I wanted to, she has, Dr. Hughes has some really nice notes on this intro, and then we're going to go over to some of our own problems. Well, it's also some of hers, but I really like the her intro for this topic. So it says sometimes, especially when you're programming, it is easiest to deal with series approximations to a function, not just the function itself. And it says, how do we get a polynomial approximation? How do we know that they are good? And this is what we're going to talk about today. So let's look at a relatively simple example. So we have this 1 plus x squared plus x cubed, so on and so on and so on. What series is this approximating? Now, the thing is, you guys actually know that this is a geometric series. And if you think about it, how much is it changing by each time? If you multiply 1 times x, you get x. If you multiply x times x, you get x squared. If you multiply x squared times x, you get x cubed, so on, so on, and so on, and so on. So if you remember from your pre-calc class, 1 over 1 minus r is how you do a summation, or how you calculate a geometric series. So we're going to kind of embrace that idea here. And we're going to say 1 over 1 minus x. So 1 over 1 minus x would be 1 plus x squared plus x cubed, so on and so on and so on. But all this really is the geometric series x to the n, right? So here's the thing. What we're saying is technically then that this is this, right? So that we could rewrite 1 over 1 minus x equivalently to the series x to the n. Now, again, just to reiterate, in general, when you're talking about a series, you're always implying that it is to infinity. And any time that you are saying that the summation goes to a particular number, like a number of terms, you're saying it's a partial sum, not a series. But sometimes I will accidentally call it a series just as a bad habit. But just so you guys know, realistically, a series is always approaching infinity, an infinite series. So we have the function f of x equals 1 minus x, and we graphed it below. Okay, so let's take a look at this graph. Okay, so if I graph g of 1, and what g of 1 means is that I take and I plug in, so I'm sorry, not g of 1, but g sub 1. So that means I go to this guy right here, to the second term. So this is the x sub 0 term, this is the x sub 1, this is the x sub 2, so on and so on and so on. So if I say g sub 1 of x, that means that I'm only going to go 1 plus x. So that means I'm going to build 2 terms, okay? If I say g sub 2 of x, I'm going to do 1 plus x squared. That means I'm using 3 terms. G sub 5, you guys get the hang of it. We're going to have 1 plus x squared cubed, fourth, and fifth. And then we graph these lines over here. So g sub 5, once again, is this guy right here, right? That's kind of the one I want to talk to you about. But I want you to notice all of these lines, okay? So if we look at f of x, that's the true line. And then we look at g prime, or I'm sorry, not g prime, g1 of x, that's this guy right here. Now, something kind of important that you guys notice, and then G2 is this guy right here. It curves a little bit. It's a parabola that curves a little bit. And then G sub 5 is this green line right here. I want you guys to notice something after I erase all this. Look at in this area right here. So in this little location right here, it seems like that G sub 1, G sub 2, G sub 5, they're all pretty darn good approximations to f of x. Right? So they approximate f of x very well at that location, okay? But as you go outside of it, you know, look at right here and right here, it's still kind of close, but now we're starting to spread out. And then you can imagine if you kept going up, this is an asymptote. Look at your height, you're getting way up here, and this guy would be continuing to go way out here, right? So we're starting to get where these values will be much different than these values over here, okay? But in here, in this location right here somewhere, like somewhere around here, it's looking pretty good. It looks like there is a pretty good, I don't want to say comparison, but it feels like the values are approximating each other pretty well in that little interval right there. Now, what we have to decide is what is that interval. So if you notice down here below, it says G1, G2, and G5 of X are all really great approximations for X values close to 0. So this is our X value close to 0 right here. So it says the more terms that we use to approximate, it seems like approximate the function, we get a better approximation. So G sub 5 is a better approximation of f of X than G sub 1 was, right? Or a better approximator than G sub 2. And you would assume that G sub 10 or G sub 20, where you get, 20 terms or 21 terms or 22 terms, that would be an even better approximator of f of X. So the more terms you have, it seems like you're getting a better approximation. So the mathematical way of asking, what is the interval of convergence? So that's what this is. So this idea is, when is it a good approximation, or where or how far out can we go? Remember I said if we continue out with this guy, and then this guy goes this way, maybe they won't be good approximations at a certain point. But right now, in a window, they are pretty good approximations, okay? So we're gonna answer this question on how to find this interval, okay? How to build this interval where we're gonna say that our graph is a good approximation of f of X, or our function is a good approximation of the original function, okay? We're gonna use the ratio test to do this, all right? So let's take a look at the ratio test, okay, and power series. So 11.8 is talking about power series, and all a power series is a series that has a variable to a power. That's in general. When I was younger, I used to think power series was so amazing because it had all this power, which it does, but it really is talking about an exponent. Okay, so we're going to say, what is the interval of convergence for 1 over 1 minus x equals x to the n, the series x to the n. So we're going to apply the ratio test to this. So if you guys recall, so let's apply the ratio test. Okay, and so we have the limit as n approaches infinity of the absolute value of x to the n plus 1 divided by x to the n. And now, if you remember, the ratio test said something very specific. The ratio test said that this limit had to be less than 1. This limit has to be less than 1 if you want to say it's convergent. So in the previous problems, you would have to find this limit. So in the previous chapters in the early sections, you would actually have to use the ratio test to find this limit. And then based on your answer, you would say convergent or divergent. But we know that the ratio test is only convergent when this is less than 1. So I'm going to say, since I'm concerned with, so since I am concerned with convergence and the interval of convergence, basically, where is the series a good approximation for the function interval of convergence? I use less than 1. So this is why in so many of the ratio test, or in so many of interval and convergence problems, you will oftentimes see that it's less than 1, and it's because we're using the ratio test. Now you could use the root test as well, but I just am more of a fan of the ratio test. I'm just better at it. But there's some problems that the root test might work just as well. So anyway, that's where I get that 1 from. It's not just made up. It's because I said that in order to be convergent, we have to be less than 1. So in a lot of these problems, you guys, and in the homework, whenever they ask you to find the interval of convergence, you'll notice that there's this 1 that always keeps appearing. Well, it's not just random. It's because that's the interval, or that's how we know that it's convergent by the ratio test. Okay. So what I'm going to do is I'm going to say limit as n approaches infinity. Now this would be the absolute value of x to the n, and that n would cancel, and that would leave me with the absolute value of x less than 1. Okay. Now, since there is no n to plug in, it kind of makes the limit a moot point. Sometimes there will be, sometimes there won't be. In this case, there isn't. So that means we really just have the absolute value of x is less than 1. And then you guys should remember how to undo this. This becomes -1 is less than x. This is a way that you can rewrite an absolute value with its bounds is less than 1, okay? So we now know that x has to be between -1 and 1. And this is now our idea of our interval of convergence, okay? So this is our concept of interval of convergence. We're saying that this is a good approximator for the function 1 over 1 minus x on the interval from -1 to 1. And if we remember the graph from the previous notes from Dr. Hughes, we see that it looked like between -1 we were okay, but we were starting to get a little bit away from being a good approximation once we started getting past 1. It was getting close around 1, but past 1, we're starting to feel like maybe it's no longer a good approximation. So we have this. Now the thing is it seems like a little thing, but the parentheses mean you cannot use -1 or 1 for your value. However, what you always will have to do is if they ask you for the interval of convergence, you must check these endpoints. So that means that I'm going to have to check if x were to equal -1, or let's do 1 first. If x were to equal 1, then we have the summation of n equals 0 to infinity of, now we're going to go up here and we're going to plug it in. We're going to use this and we're going to plug in 1. So this would become 1 to the n, okay? And 1 to the n is just going to equal the summation of 1 This is divergent because, as you can imagine, the limit of this is not 0, so it fails, or it allows us to use the divergence test. So this diverges by test for divergence, since limit as n approaches infinity of 1 equals 1, which is not equal to 0. And that's what the divergence test says. It says if x is equal to -1, we get n equals 0 to infinity of -1 to the n. But this diverges also by the test for divergence. Okay. Okay, because that limit is also not 0. All right. So we can now say definitively that our interval of convergence is from -1 to 1. This is our interval. I'll just write it in abbreviations. Interval of convergence, IOC. Okay. So we were not able to put brackets on the -1 or 1. The other thing that sometimes gets asked as well is our radius of convergence, and sometimes they'll call it big R equals 1. Okay. So how far is it from here and how far is it from there? It's a distance of 1. A lot of times you can tell is once you've gotten the absolute values around the x and the x alone without any multiplication or division, then whatever number over here turns out to be your R. Okay, but if it was like 2x, then our radius of convergence would have been 1/2 because we would have needed to divide the 2 over. Okay, so this is one way that you can deal with radius of convergence. The good thing is the radius of convergence is actually better if they ask than the interval, because if they just ask for the radius, then you don't have to do this part right here. You don't have to test the endpoints. They just want to know the radius of convergence. You just say 1 and you're done. But if they ask you for the interval of convergence, then you not only have to find the interval, which is this, right? But then you also have to test the endpoints. And in this case, it was easy, but in other problems, it's more difficult. Okay, so let's look at another problem. It says find the interval of convergence for n equals 0 to infinity of 2 to the n x minus 2 to the n all over n 3 to the n. Okay, so this is a much tougher problem. So let's set it up in the ratio test. Remember, that's your, whenever they ask you for the interval of convergence, so they ask me for the interval of convergence, this is your go-to. You just jump straight into this. Okay, so we just do the limit as n approaches infinity of 2, absolute value of 2 to the n plus 1 times x minus 2 to the n plus 1, all divided by n plus 1, 3 to the n plus 1, times the reciprocal of the original, which would be n 3 to the n over 2 to the n x minus 2 to the n. And we know this has to be less than 1. So now we're going to have to do a little bit more work. So this x minus 2 to the n is going to cancel with this x minus 2 to the n, and it'll leave us with the plus 1. This 3 to the n plus 1 will cancel with this 3 to the n, and it'll leave us with this plus 1, 3 to the 1. This 2 to the n will cancel with this, and we're left with that. And I think that's it. And we're still going to be left with this n and this n because we can't cancel those. So this will be the limit as n approaches infinity of the absolute value of, let's see here, 2x minus 2 to the 1 times n all over, let's see here, 3 n plus 1. What else do we have left? I think that's it. So that is actually it. Let's see here. So I believe I'm going to be left with the limit as n approaches infinity. So I can take the 2/3 out of the absolute value, and this will be left with x minus 2 over 1. And now the n is always going to be positive, so the absolute value doesn't affect that either because n is approaching infinity. So this will be n over n plus 1, and this will be less than 1. So then let's say the limit. Now hold on a second. You guys know that technically I'm supposed to take the limit of each piece, right? But I'm just going to kind of cut to the chase. And I'm going to say, well, if I take the limit of this, right, because that has all the n's in it, I could technically take the 2/3 out in front of the limit. And we know that when you have same powers and you're taking the limit as n approaches infinity of a rational expression, we know that you can just take the leading coefficients and divide them. So that'll actually just be 1. So we're going to be left with 2/3 times the absolute value of x minus 2, because it has nothing to do with n, right? So we can take that out of the limit, or we could take the limit of it and it would not do anything. You know what? I feel like I'm skipping a step, so I don't want to mess you guys up. So we're going to do this. We're going to do 2/3 absolute value of x minus 2 limit as n approaches infinity of n over n plus 1. Let's do that. And now we know that this will cancel and become 1 when we take that limit, and this has to be less than 1. So this will be 2/3 absolute value of x minus 2 less than 1. All right, so this is all gone now, and it becomes 1. Okay, no more limit. We used up the limit by taking the limit of n plus 1. So now we just have to solve for the x minus 2 inside the absolute values. Just multiply 3 over 2 over to the other side, and then put a 3 over 2 here. So now we have the absolute value of x minus 2 is less than 3/2. So this, by the way, is my r. Okay, that's my radius of convergence. Okay, but they asked me for the interval of convergence. So what I'm going to do is I'm going to take x minus 2, and I'm going to do this less than and less than, make it a compound inequality. I'm going to put negative 3/2 and positive 3/2. Remember, this is how we undo it. And then we plus 2, plus 2, plus 2. So we end up with, let's see here, 3/2 plus 2. So this would be 1/2 is less than x, oops, is less than, what is that? Let me see, 2, 4, 7/2. So we have 1/2 is less than x is less than 7/2. So these are the values that I want to use as my interval of convergence. So this is my interval of convergence, but remember, I now have to double check and see if I'm supposed to use bracket or parenthesis. So I'm going to come down here and I'm going to say if x equals 1/2, then we have the summation of 2 to the n. And remember, this is values of x. So remember, it was x minus 2. So this is going to be 1/2 minus 2 to the n. Okay, and then all divided by n3 to the n. Well, this is going to equal, let's see here, n equals 0 to infinity. Well, let's see. This is going to be n equals 0 to infinity. This is going to be 2 to the n. This will be what, 3/2, negative 3/2 to the n, all over n3 to the n. Now it's going to get kind of clean right here. Everything's going to clean up because this is really -1 to the n, 3 to the n, divided by 2 to the n. If you distribute the n to everything, right? So then that will cancel this guy with this guy, this guy with this guy. So basically all of that's going to cancel, and we're going to be left with the series n equals 0 to infinity of -1 to the n. Is there anything left standing? -1 to the n, and I believe we still have that n right there, okay? However, you guys know that this is the same as this series of -1 to the n times 1 over n. And that should be a familiar one that we've done before. This is convergent. So this is convergent by alternating series test, right? That's one that we've done in the past. I think that was even on one of the exams, something simplified to that. So we know that that's convergent. So then when we're using 1/2, we're going to need a bracket. And now let's check 7/2. If x equals 7/2, then we have n equals 0 to infinity. And we're going to go 2 to the n, 7/2 minus 2 to the n, all over n, 3 to the n. Now there should be something very similar. We're going to have 2 to the n. So this will be what? 3/2, right? Because that's 4/2, so that'll be 3/2. 3/2 to the n, all over n, 3 to the n. But that's going to be, and the same stuff's going to happen again. This is going to cancel with this, and this is going to cancel with this. But this time, we end up with 1 over n, which we know is divergent by, you could say p series, or it's a harmonic, so it's a divergent series as well. So that means our actual interval of convergence is bracket on the 1/2 and a parenthesis on the 7/2. Okay, so these are things that you actually have to double check. It seems like a little thing, but you're saying that 1/2 is included in your interval of convergence. It's still a good approximator, but 7/2 is not. Okay. So I think that's enough for now. If you want, we can go over another one in our next meeting. I just want to talk to you guys about a few special cases. Okay, so what if we have, it's not just saying that this is the only special case, but I just want to show you an example. So an example of a special case. So suppose we have this series. I want to show you something that happens with this. N equals 0 to infinity of x to the n over n factorial. Well, we know that we're going to do the limit as n approaches infinity of the summation, oops, sorry, wrong part, x to the n plus 1 in absolute values divided by n plus 1 factorial times the reciprocal, n factorial over x to the n, and we know that has to be less than 1. So we know that this is going to become limit as n approaches infinity, and this will cancel with this, and we'll be left with the absolute value of x, and this factorial will cancel that, and we'll just be left with n plus 1 is less than 1. And again, if you don't believe me, you can write it out. This is n times n minus 1 times n minus 2, so on and so on. This is n plus 1 times n minus 1 times n minus 2, so on and so on. And all of these will cancel with all of those, and this will be the only thing left. So that's how you can kind of clean up factorials pretty quickly. Hopefully you are getting better at that. So we basically have the absolute value of x over n plus 1, but remember n is always positive, and when you add 1, so it doesn't need, it's a redundancy. So we're going to say that this is the absolute value of x, which has nothing to do with the limit as n approaches infinity of 1 over n plus 1 is less than 1. But you guys know that this is actually 0 because the limit as n approaches infinity of 1 over an infinitely large number is going to be 0. So then we're going to have the absolute value of x times 0, okay? But you know that no matter, now think, whatever you pick for x, are you always going to be less than 1? Well, yeah, because 0 times anything is going to be less than 1, I mean, besides infinity, okay? So this will actually then lead to an interval of convergence from negative infinity to positive infinity. So whenever the limit becomes 0 like this limit right here becomes 0, you probably are going to just have some nice quick answer like this, and your radius of convergence would equal infinity, okay? Now let's look at another example. This is kind of like the, almost like unnecessary one, okay? So I don't want to say unnecessary, that's a bad way to say it, but it just feels like it's not really what we're looking for here. So we have n factorial x minus 4 to the n equals 0 to infinity. So it says find the interval of convergence. What would the ratio test yield? So we would say the limit find the interval convergence. So we'd say the limit as n approaches infinity of the summation of n equals 0 to infinity of n plus 1 factorial. Oops, what am I doing? Sorry, guys. Sorry. Limit as the absolute value of n plus 1 factorial x minus 4 to the n plus 1 all over n factorial times x, or over x minus 4 to the n, has to be less than 1. But there's going to be some really nice cleanup in here, obviously. So you guys see this is going to cancel with this, and we'll be left with the 1. And then we know that this n factorial is going to cancel that factorial. So we're going to be left with the limit as n approaches infinity of, now let me see. We'll have the absolute value of x minus 4 times, what is it, n plus 1? And less than 1. So we can clean this up a little bit. We can do the absolute value of x minus 4 times the limit as n approaches infinity of n plus 1 is less than 1. But you guys notice the problem right now, hopefully, is this will always be infinitely large. So what's the only chance we have of this ever being less than 1? Well, this is going to be an infinitely large number. And the only possible situation that could ever lead to this being less than 1 is if x were equal to 4, because then you'd have 0. So if x were equal to 4, or I'm sorry, x equals 4 is our interval of convergence, which doesn't even feel like this is really an interval, right? It's just x equals 4. So this would be our answer. So this isn't really ideal for what we're going for. I would say most problems, you actually get an interval of convergence that's an actual value instead of just one particular number. But I just wanted to show you guys these two kind of special scenarios that can happen. Okay. So now, let's see how much more I want to cover today. So we have a little bit more to do today. So what if I asked you to find the power series for 1 over 2 plus x cubed? Okay. So this is going to lead us to an idea, okay? So the thing is in all those previous problems, I was asking you to find the interval of convergence for a particular power series. But what if I gave you a function and I wanted to know what is the power series for this function? We need a way to develop this, okay? So we're going to focus on a power series for functions that can be written in a specific form. So our form is 1 over 1 minus f of x. Okay, this will be our form, and this will be equivalent. So if we can write the function like this, exactly like this, this is 1 plus f of x quantity squared plus f of x quantity cubed, so on and so on. And it turns out that we can say that this is equal to the infinite series, or to the series n equals 0, to infinity, oh my gosh, to infinity of f of x to the n. So what this basically saying is, if you can ever write it like this, if you can ever write your function like this, then you can just switch it to a series. You can rewrite it as this, okay? So whatever your f of x is, you just take it to the power of n. So let's use that thinking over here. So we have 1 over 2 plus x cubed. So I need to find a way to write this as 1 over 1 minus f of x. That's my goal, okay? So I could factor out a 2. So this would be 1 over 2 times 1 plus x over 2 cubed. Let's see if this works. Now, if I take 2 and multiply it by that, I get 2. If I take 2 and multiply by that, I get x cubed. So you guys see what I did there? That's the technique that you're going to use a lot. Okay, that's the technique you're going to use often. Okay, is you're going to factor something out and rewrite it. Okay, now here's the thing. This is actually, so let me do this. Let me write it better. So then we have, okay, maybe I should do this. We want this. Okay, so we're going to take 1 over 2 plus x cubed, and we're going to say that's the same as 1 over 2 times 1 plus x cubed over 2. But now it also says that I want it to be a minus sign in the middle. See this minus sign right there? So then I actually need this to be 1/2 times 1 over 1 minus a minus x cubed over 2. Now let's see. If I take the 2 and I distribute, I would get 2. And if I take 2 times a negative negative, I would get x cubed. So this is still fine. This is still correct. So the power series representative of 1/2 times 1 over 1 minus negative x cubed over 2 could be rewritten as this power series. 1/2 times a power series n equals 0 to infinity. And now again, I'm looking at my f of x. Notice I have it written the same as right here. I have this minus f of x right there. I have this minus f of x right there. Or I'm sorry, let me clean this up. I have the minus f of x. I have the minus f of x. So then it says that I can just take f of x and put it to the power of n. So I'm going to do that. I'm going to say f of x is negative x cubed over 2 to the power of n. Okay, so now let's clean this up, and I will ask you guys to, in general, clean up your summations. Don't leave it like this. So this would be 1/2 n equals 0 to infinity of negative 1 to the n, x to the 3n, all over 2 to the n. And we now know that this is equivalent to 1 over 2 plus x cubed. We know that these two things are identical. So we have a function and we found its series representative, all by converting it to 1 over 1 minus f of x. So it has to be identical to that. It must be the same, okay? Okay, so let's try one more. This is definitely something you need to practice, okay? So let's do find, so I hope you guys see the point is the beginning of this part we were trying to find the interval of convergence when the power series would be a good representative for some function. Now we're saying we have for our particular function. Now we're saying, what if I gave you the function? I want to know what power series made it. So you're not only just checking a power series, you're actually building the power series yourself. Okay, so find the power series for 1 over x squared minus 3. Okay, so you remember that we want 1 over 1 minus f of x, because if we can write that, then we're good. Okay, so I'm going to have to do some cleaning here. I'm going to do 1 over negative 3 plus x squared. So I'm going to rewrite it in the better order. But this is actually 1 over, and now I'm going to factor out a negative 3, and that's going to leave me with 1 minus x squared over 3. So now and again, you guys kind of got to get comfortable with this. This isn't everybody's ideal way to do it, but remember, I know this was legal to do because if I distribute this back, I get negative 3, boom. If I take negative 3 times this, I get positive x squared, boom. So I didn't do anything wrong. I just distributed in a funny way, or I factored out in a funny way, and I checked it with my distribution. Okay, so now that means that I should be able to write this as negative 1/3 times the power series. And remember, I have 1 minus f of x, right? So that means my power series this time is x squared over 3 to the n. No negative this time. But then this is negative 1/3, oops, n equals 0 to infinity of the series, n equals 0 to infinity. Now I'm going to clean this up a little bit. This is going to be x to the 2n all over 3 to the n. Okay, so and then what will expand is then once you have this, then it'll say, oh, now find the radius of convergence for this series that you just built from scratch. Okay, so hopefully you guys understand that what we just said is that this power series is now equal to 1 over x squared minus 3. Now we haven't found an interval of convergence for it yet, but I want all of your x's and your n's on the inside of your sum. You cannot have them outside the sum. So anything that's on the outside better be a constant, okay? So please make sure you do that for these particular problems, okay? I think I'm gonna end that for the video. I have a few problems that we'll talk about in class when we have time that are, you know, little variations of this, but that's a long enough video for this one. All right, you guys, see you in the next meeting.